Hello everyone, welcome to the pH and buffers video. So let's begin by talking about the pH scale. The pH scale ranges generally from 0 up to 14, though you'll occasionally see negative numbers in solutions that are extremely acidic, or you might see numbers over 14 in solutions that are extremely basic, but generally most of the time we're between 0 and 14. And so contrary to sort of popular misconception, a high pH actually means basic and a low pH means acidic. And a pH of 7 is considered to be neutral. So pure water is going to be neutral. Drinking water has a pH of around 7.2. That's because of the dissolved minerals. Rainwater is actually slightly acidic due to the dissolved carbon dioxide. And we can see various things here. Seawater is around 8.5 because of the dissolved minerals. Things like bleach or Drano are very basic here, down at the higher end of the pH scale. You'll notice that most foods are actually acidic. So we have things like apple juice and coffee and such that are acidic. Oranges, 3.5. And the lower our values here, the more acidic the solution. We see that soda is actually quite acidic. It often has both carbonic acid as well as phosphoric acid in it. And then 1 molar HCl solution would have a pH of 0. So how do we measure pH? Well, there's a couple ways of doing it. We can use a pH meter to test the pH. Or we can use pH strips. These are going to change color, and so the color is going to vary depending on the pH of the solution we dip them in. Or also, you might remember that the cabbage in one of our previous labs changed color when we exposed it to acids or bases. The cabbage actually is an example of a pH indicator. And we'll be using another pH indicator in the titration, and come to think of it, we used that same pH indicator, the phenolphthalein, in the same lab as the cabbage when we were adding acids and bases to it, making it change color. So we have a few methods of measuring pH depending on what we're trying to do. I want to make a quick comment on significant figures in regard to pH. I'm not going to be very picky when it comes to this, but essentially, if we have a number in terms of concentration of hydronium that's known to one significant figure, then we're going to have one decimal place in our pH value. If we know our concentration of hydronium to two significant figures, then we'll have two decimal places. And that's because essentially in the pH measurements, the logarithmic measurement, only this decimal portion, the portion to the right of the decimal point, is actually part of our number. It's a little strange. I don't need you guys to be real concerned with those rules, but just a heads up, you might see this in questions in mastering. So right here, we have an example problem. Find the pH of a solution with concentration of hydronium of 1.7 times 10 to the negative third moles per liter. The equation we use is that pH equals the negative log of our hydronium concentration in moles per liter. And I know it's scary. We have logarithms for the first time, and you're going to have to use the log button on your calculator, but you'll get the hang of it. And these slides here are a good place to check to make sure you're doing it correctly. So enter in negative log of this value right here. You might need to use parentheses or brackets to get it to work out properly with the scientific notation, and you should end up with the value of 2.77. And again, because this is known to 2 sig figs, we know this to 2 decimal places. So we're going to go in the opposite direction now. The previous slide had the equation for going from concentration of hydronium into pH. This one's for going from pH into concentration of hydronium. So we're asked, what is the concentration of hydronium for a pH value of 8.25? So our equation is concentration of hydronium equals 10 to the negative pH. And so if our pH equals 8.25, we'd enter in 10 to the negative 8.25. And again, you'll have to figure out how to do this with your calculator. And since we have 2 decimal places here in our pH value, that means we'll know our concentration here to 2 sig figs. I'd like you to now pause the video and please complete questions 1 through 5 on the worksheet. Welcome back, everyone. Let's talk about buffers. So buffers are mixtures that are going to keep the pH of a solution relatively stable. So they're going to maintain our pH by neutralizing any incoming acid or base. So they have components that can absorb and neutralize the hydronium coming in, as well as components that can absorb and neutralize the hydroxide coming in. And so these are actually incredibly important because the pH of a biological system must remain very steady. If the pH of a biological system changes, then the proteins and enzymes are going to get all denatured and they're not going to work anymore, and essentially the organism will die. So here we have an example. Let's say we take distilled water and we add even just a tiny amount of acid. We're going to see a pretty massive pH shift up to or down to 4.0 here, with even just a small amount of acid added. And similarly, if we add even a small amount of strong base, we're going to go up to maybe, let's say, 10.5 hypothetically. So even small amounts of acid or base will dramatically shift the pH of a solution of water. However, if we take a buffer, and this particular buffer has a pH of 7, but they're not always 7, and we add a little bit of acid, our pH is just going to shift ever so slightly. So now we're going to go from 7 down to 6.9, so only a very, very tiny shift. And if we add a bit of base, we're going to end up again with a very tiny shift. We'll go from 7 up to 7.1, so we don't see the type of dramatic changes we saw with the pure water. So the pH will still shift, but much, much, much less than it did with the pure water. So what components are in a buffer? Well, a buffer is usually going to be acid-base conjugate pairs. And so we're going to want a weak acid and the salt of its conjugate base. Or we can have a weak base and the salt of its conjugate acid. So we mentioned before that the weaker the acid, the stronger the conjugate base. So what this means is our weak acid can neutralize any incoming bases that we add. But we also have this base present, so this conjugate base will actually be able to neutralize any incoming acids. And similarly, we can kind of do this with bases as well. It's a little less common, but we can use bases. So we can use a weak base and the salt of its conjugate acid. You might see these as well, but just not as commonly. So if we look at a specific example here, acetic acid is an example of a weak acid. And we're going to combine it with the salt of its conjugate base, in this case sodium acetate. And people usually use the sodium salt because the sodium salts are always soluble in water and they're cheap and non-toxic. So like, why wouldn't you use sodium? Sodium is cheap, it dissolves, it's not poisonous. And so we're essentially just going to mix together a bunch of acetic acid and a bunch of sodium acetate, and it actually works best if we have a 1-to-1 ratio of those in terms of moles. And so what we end up with is this mixture now that contains both acetic acid, so weak acid, as well as its conjugate base, these acetate ions. And so now if we take this mixture and we add a strong base to it, like hydroxide ions, those acetic acid molecules will neutralize the incoming hydroxide to form more acetate ions as well as water. So before we started, if we had an equal mixture of acetic acid and acetate ions, we add some base, we now have less acetic acid and more acetate ions, more conjugate base ions, but our pH hasn't changed much. So we did use up some of our buffer, but the pH remained relatively steady. So we can also add acid to our mixture here. So again, let's start out with an equal mix of similar number of moles of acetic acid and these acetate ions. We add our strong acid, our hydronium ion source, and we're going to create more acetic acid, get rid of some of our acetate ions, so this concentration goes down, this one goes up, so we've used up a little bit of our buffer, but our pH has remained relatively steady through this process because we've essentially neutralized that incoming strong acid. So in summary here, if we add a strong base to our buffer, the acidic component is going to neutralize it, and we're going to only change pH slightly. If we add a strong acid, the basic component of our buffer is going to neutralize it, and the pH will remain relatively steady. And it's really kind of hard to imagine these things actually working. It kind of sounds like magic or something a little bit, but they work quite well. And so the last lab we'll be doing will actually be testing some buffers and making some buffers, and you'll be able to see that they do indeed work. So I'd like you to please pause the video and complete questions 6 through 12. And once you've done that, I advise that you go on over to the discussion board and discuss with your classmates. Thank you. Bye.